Proszę Państwa, zacznijmy zatem od tej prezentacji. Now it's time for the first presentation of the day. IP-over-DWDM systems and 100, 400, 800G coherent optical transceiver in a nutshell. Everything you need to know to take the best from them for your network. This topic will be brought to you by Marcin Bała, CEO of Salomanus, and Andrzej Wojnar, Solution Architect at Salomanus. And what will they talk about? They will talk about the pros and cons of IP-over-DWDM systems, monitoring and management challenges. They will also present the example applications. The stage is yours.
Hello, everybody. It's really nice to have so many guests in my birthday, because it's exactly that day. So let's start. The key story of technology is full of revolutionary changes that today seem trivial, but at the moment of implementation were groundbreaking. Think about computer mouse, personal printer, or touchscreen. Similarly revolutionary, although we may not yet realize it, is wavelength division multiplexing in transmission, or more specifically, EDFA amplifier, which contributed significantly to the development of DWDM. Performance, capacity, range. Without this in transmission, we wouldn't have so easy access to all types of information that we do today.
So on today's presentation, first of all, we will focus on the DWDM system, how we build the traditional system and how it works. Then we will talk about the evolution in that technology and where this evolution will bring us and what alternatives we have today. Later, we will try to find the answer for the question if coherent transceiver will bring the revolution today, if it's a game changer. Of course, we will also highlight the most important application, and we will end up with some conclusion and benefits of using the new technology available on the market.
The first commercial implementation of WDM system, which transmits data using parallel channels created in the same optical fiber by using light stream of different wavelengths, occurred in the middle of 1980s. It was just two channels, 1310 nanometers and 1550 nanometers, and area around the second wavelength, 1550, became the main focus for such systems when relatively inexpensive semiconductor lasers appeared on the market, emitting light within this range. The second reason is that silica-based fiber has the lowest attenuation in this area and easy to compensate the chromatic dispersion. The initial solutions offered from 2 to 8 channels, but within slightly more than a decade, by the end of 90s, we already had the systems with more than 64 channels, with channel spacing 100 gigahertz or 50 gigahertz, which we know actually nowadays also.
A very important component of the traditional DWDM system is transponder. Transponder have few roles in the system. First of all is the border between the optical layer and the layer of services we transfer from either customer or either from internal customers, so from IP devices in our network. The other role of those devices is also coloring the signal. So on the client side, we use the gray or direct detect optics. On the line side, we use the colored optics. Of course, the other version of the transponder could be also maxponder, which will help us to have a better use of the passband of the spectrum we will have there. The other components are the optical line system. When we look on the optical line system as an overall, we will have there the few components like multiplexer, like ROADMs, like EDFA, and the DCM. The last one we could eliminate from the network when we decide to build a network which is fully coherent.
The revolutionary discovery we mentioned previously is EDFA, erbium doped fiber amplifier, which made a huge revolution in signal transmission, allowing for significant distances to be achieved. Nowadays is essential element of DWDM systems. The second revolution came already in 21st century with coherent modulation. Higher transmission speeds require higher signal frequencies, which created more and more technological and engineering challenges and limitations related to transmission and modulation of those high-frequency electrical and optical signals. Therefore, we started to use coherent modulation, much more effective modulation, which utilizes not only the amplitude, but also phase and polarization of the signal to encode transmitted data. The result of this modulation is transmission of constellations, point arrangements we use to encode transmitted bit sets. This change introduced the usage of DSP signal processors, digital signal processors, necessary to decode transmitted information in real time, and generated significant changes in network architecture we will show in a moment.
So to sum up the traditional approach of building the DWDM networks, we need to highlight that those solutions are really effective because of the whole portfolio, muxponders, transponder, and all around, they are really effective. But despite of that, we have also some limitation of going into the closed and single vendor approach. First of all is the centralization. So usually we have the dedicated racks which need to be exchanged with every new generation of technology coming to the market. We also, because of those, we also have some delay in adapting the new technology because we need to design the new specific chassis, we need to upgrade the cards which exist in, and all those generate delay. The other point is that the architecture usually is very close. It means that we have difficulties to run the even alien wavelength services on such network because of the limitation of the management system, limitation of the RADM input or multiplexer. And on top of that, we very often have the complex licensing, which end up that at the end of the day, we don't really control the operational cost of those networks. As an alternative to closed and traditional DWDM system, we have open and disaggregated networks, which allow us to build a network with multi-vendor equipment. Of course, we need some standards behind. One of the first approach to do that is going to IP-over-DWDM technology. This technology allows us to eliminate transponder, muxponder, and install the coherent transceiver directly into IP devices.
The concept of IP-over-DWDM is more than 20 years old. However, its practical implementation was not possible before due to the lack of optimal components. Because the first coherent DWDM transceivers necessary for realizing this idea were power-hungry beasts enclosed in huge CFP housings. The reason was extremely high power consumption of digital signal processors. As I mentioned, the essential element of such coherent modules. Modern lithography processes used in semiconductor manufacturing allowed for significant miniaturization and reduced the power consumption of DSP, which allowed for construction of such modules in quite compact QSFP-DD or today even QSFP28 housings. Such interfaces allow for high port density in routers and switches. Today's offering of coherent modules is already very extensive. It includes 400G transceivers, 100G transceivers, QSFP28 from this year, and in the next year we will have 800G coherent transceivers. The roadmaps already shows the 1.6 tera coherent transceivers. Please note that successive generations of the modules with the same transmission speeds are characterized with significantly lower power consumption and much longer transmission range.
So all those open networking and IP-over-DWDM is only possible because we have some standardization behind. These standards already have some history. Some of them were announced first time 8-9 years ago. Some of them, they are newer. But when we take about closer look about that. So first of all, when we talk about the coherent transceiver, we have few standards which helping us with deploying those in our devices. So when we look into the communication between host and transceiver, we have all CMIS and Systemy standard related. Systemy is extension of CMIS, of the Common Management Interface specification for the coherent parameter. But this guarantees us the interoperability between host and transceiver. The other part of those transceivers is interoperability on the optical path. And when we look closer to that part, we have two options. First one is the standard relay on OIF 400ZR. This could address our need to provide the links with the distance up to 120 kilometers. If we have longer links with a little bit more flexibility, we have OpenZR Plus standard, which cover much more. So this will be the pluggable, this will be the optics. The other is other components we are using to build the networks, like ROADMs, like EDFA, like other equipment that build in the layer 0 of the network. Here, we could benefit from Open ROADM standard, which allow us to do that. So if we have all the components which are standardized between them, the only one necessary things we need is the system to manage that. And here we also could rely on a little bit old one, because the history is almost 20 years, which is NetConf with data model Young. This one will allow us to build the open disaggregated networks, which help us to gain because of the cost efficiency, because of introducing the new technology much faster to the market.
One could ask why we're making this revolution with IP-over-DWDM. What for? The answer comes from the data presented by the customers who decided to implement this technology already a few years ago. And as you can see on this table, we have here comparison of investment costs, energy costs, and rack space utility, depending on different connection methods in DWDM systems. As you can see, the connection made with 400G ZR Plus coherent modules is the most favorable in case of those parameters. We are able to save up to half of the investment costs, 70% of energy costs, and half of the rack space. Data provided by another IP-over-DWDM users shows quite similar savings.
When talking about IP-over-DWDM, which is first step to build our network a little bit more open, we need to take a closer look to our network, because very important will become the monitoring the optical parameter, like the one provided by OTDR or optical spectrum analyzer, to not be blind. Because very often when building traditional DWDM network, we give up those optical measurement devices, because some optical monitoring we were able to achieve directly from the transponder or maxponders from the line side. But with the open networking, with IP-over-DWDM approach, we will not install any more transponder, because optics will be installed directly into IP devices. So that's why the OTDR, the optical spectrum analyzer, the optical monitoring of the link will become even more important.
Enough theory. Let's dive into the real applications we are able to build based on this technology. For the beginning, something a bit different. IP-over-DWDM is not only the long-haul transmissions and powerful coherent modules. Sometimes we need much shorter distance and n times 100G transmissions. In such scenario, the passive O-band solution would work perfectly. We have QSFP28 100G modules installed directly in routers and switches, and with totally passive multiplexers, we are able to transfer up to 16 channels on a distance 20-25 kilometers. Please note that thanks to the wideband receiver of those transceivers, we are able to implement this scenario also in single fiber systems.
The 100G ZR 100G coherent transceiver is finally available in the market. And together with that availability, we are finally able to migrate our legacy 10G network to 100G network in a very easy way. Why this is possible? Because 100G coherent transceiver, first of all, is in QSFP28 form factor, so the form factor which is very popular on the market. Secondly, the TX and RX output power and sensitivity are even better than the one provided by 10G transceiver. Similar for the chromatic dispersion compensation. This one is not 1,600 picosecond like for 10G transceiver, but even 2,400 picosecond. So this makes us very easy to upgrade the existing network to 100G just by replacing transceiver of the both end and keeping our optical layer not changed. With coherent transceiver, we are able to build the DWDM network even in easier way. Because the receiver of those transceivers is selective, we are able to skip installing the multiplexers. Instead of that, we could use just passive optical splitter to combine few wavelengths into one fiber. If we don't have enough power budget to reach the longer distance, that's no longer issue. Because two fully automated EDFA, we close into QSFP form factor transceiver for easy powering up. So in fact, we need just passive splitter, few 100G transceiver, and the EDFA which is also built into QSFP28 transceiver, so just one more QSFP slot to build a fully optical layer n times 100G.
Now something from higher weight category. One of the simplest application of QSFP-DD 400G coherent transceivers is the connection between two data centers with several or dozens of 400G connections. Even such simple application like point-to-point connection could have several variants. The simplest one, totally passive, when we are using passive multiplexers and coherent modules installed directly in network devices, could handle up to 16 channels over the distance of 30-40 kilometers. With pluggable optical line system Marcin mentioned on previous slide, we are able to transfer up to 12 channels over the distance up to 120 kilometers. If it is not enough, we need to use multiplexers with 75 or 100 gigahertz grid and EDFA amplifiers to amplify the transmission.
0dBm OpenZR Plus is already available on the market for a few years. And this 0dBm is very important because 0dBm allows us to bring those transceivers to the existing network, so allow us to do the brownfield deployment. What is very important, 400G OpenZR Plus transceiver is not only the transceiver which gives us 400G speed on the line side. The feature of those transceivers is pretty similar like transponder, so if we want to make a longer link, we could reduce the speed, change the modulation on the line side, change the forward error correction methods to obtain the longer links. So we could go to 8 QAM and get 300 gigabits. We could go to QPSK and have 200 gigabit line speed and having the very long distances, similar like approach for the transponders. What's very important, all those settings, thanks to CMIS and CCMIS extension, are available from the command line directly from the host where the transceiver is plugged in.
400G ZR Plus transceivers, or another area where those transceivers could be used is access and aggregation network. In this area, we often suffer from the limited availability of QSFP-DD ports. But devices in this network area are dominated by QSFP28 ports. How to deal with this? In this case, standardization, Marcin mentioned, come to help us. because on the core network side, where we have enough QSFP-DD ports, we install QSFP-DD 400G ZR+ transceivers, but on the access and aggregation network side, we additionally use the MaxPonder with 4 or soon with 8 100G ports. And on line side of this transponder, we install exactly the same transceiver like on the core network side, but using this transponder, we connect access and aggregation devices with standard QSFP28 100G transceivers, any types, short range, long range, even coherent QSFP28 we mentioned before. Such solution could significantly extend the life of these aggregation and access devices, preventing from necessary migration to higher transmission speeds.
The transponder Andrzej mentioned, the youngest kit of our product portfolio, which come to the market in next year, is the universal transponder, which is equipped with 10 800G QSFP-DD ports with fully non-blocking matrix. What for we decided to develop such transponder? First of all, we have idea in our mind to make the solution open and universal. So the basic idea is that even if our switches or routers are not equipped yet with 800G ports, we could use QSFP-DD transceiver with coherent feature on the line side. And then later when we upgrade our router or switches, we just take the same transceiver and plug it into the host, which we are not able to do when we decided to use the transponder with CFP2 on the line side. Non-blocking matrix allow us to implement a lot of application. You have the plenty of them presented on the slide here. And the very important is that we have one extra feature. We could combine 2 line transceiver using the Y cable to obtain 2 times higher speed. So in using just Y cable. So that one gives us opportunity to run 1.6 tera coherent lambda even today, without waiting until those transceivers will be available to market. And what's very important, we will got those parameters with the OSNR level required for lambda 800G, not 1.6 tera, because we are just squeezing 2 lambdas as close as possible to each other, so we occupy the same frequency. And what's very important, we are using the standard transceiver, so the transceiver which could be also plugged to the host in the near future.
So, to summarize, IP-over-DWDM could be a perfect way for increasing the competitiveness through the better use of available budgets. By the savings on infrastructure and energy costs, we are able to build more efficient network and extend the competitiveness thanks to this. IP-over-DWDM is already mature technology which fits perfectly into the growing trends of open optical networks, interoperability, and disaggregation. Coherent optical modules are nothing scary. They become already more and more popular in many network areas. And for lots of possible implementation of this technology, we need just 4 universal components: 400G or 800G transceiver, 100G transceiver, universal transponder, and our SRD environment to make the universal transceivers compatible with any brands of the network devices used in your networks.
So in our opinion, IP-over-DWDM is technology no longer only for enthusiasts of something which is new. It's already major technology. This technology already crossed the Moore's chasm, and it's mature, it's available for the market for deploying today. This technology even if this technology brings some challenges, even if it requires us to redefine the way we build in the network today, remember the first slide, the printer, EDFA, touchscreen. The history of technology is continuous chain of revolution, and the people like us are to make those technology more familiar.
And as a last slide, we are obliged to show you information about co-finance project with EU funds, with European Union funds, which support us in developing some of those transceivers, because within this project we developed 100G and 400G transceivers, so we are showing the information about this. Thank you very much.
Thank you very much.